Welcome to the final presentation of StaRS filter theory. StaRS stands for Stacked Rapid Sand. My name is Barbara Rama. I'm a junior in environmental engineering and I am sub-team lead, and here are my team members.
I'm Lainey Reed. I'm a sophomore in environmental engineering.
And I'm Emily Speck. I'm a sophomore in chemical engineering.
So stack filtration occurs as one of the last points in an autoclave plant, and we are, as a team, we are looking at developing a mathematical model to increase filter efficiency, and we will be doing that by varying different types of parameters. So the focus of our team this semester has been looking at how varying diameter of sand particles will affect filtration.
So our team started this semester off as all new team members, so we spent the month of September learning about how filtration works and how stacked rapid filters work. And we did that by looking at past projects and existing literature. We also had to complete several trainings so that we could work in the lab. We spent October redesigning the apparatus, so we started working with the original one so that we knew how it worked, and we started to design the new one. And then finally we began constructing the new apparatus.
So in November, we continued fabricating our new apparatus, and we also obtained 3 different sand grain sizes for our new filters. And then in December, we wrapped things up by writing our final report and working on our final presentation.
So here's some technical terms we believe are necessary for you to understand before going into the presentation fully. So the active zone is the site in the filter where filtration is occurring at that point in time. And an active zone, it moves down through the filter until there is no more pores, there's no space for particles to clog. And the ripening time is defined as the time in the beginning, when the filter begins, for it to reach maximum filter efficiency. And then failure time is the time taken for the filter to have, we see an increase in effluent turbidity, and that's an indicator to us that our filter is no longer performing at maximum efficiency. And then backwash, this occurs at the end of the experiment, and this is the process where there's an upward flow of water to remove any of the flux from the pores in the sand.
So here's how filtration actually works inside a stacked rapid filter. So the flocks move between the sand grains and they stick to the sides. And so they start to form these constrictions that are in the shape of a washer. And so in this constriction, the shear force increases due to the smaller diameter. And so the shear force becomes so great eventually that the flocks can no longer stick inside of that washer shape. So they start to stick in the pores that are lower down on the column, and that's how the active zone moves throughout the column. So eventually the active zone reaches the bottom of the filter, and that's when it fails. So we are actually looking at the relationship between failure time and sand grain size. So past teams have looked at the relationship between flock size and coagulant dosage and failure time. So they found that a range of coagulant between 0.02 and 0.1 milligrams per liter is the ideal coagulant dosage and for maximizing the failure time. So we believe that these smaller sand grains will increase the failure time because larger sand grains have less pores in the same volume, so the active zone will move through quicker.
So this semester, as Lainey mentioned, we moved our focus to figuring out how different sand grain sizes affects filter performance. So in order to do this, we had to redesign our apparatus. Before, we only had 1 filter, but now because we have 3 different sand grain sizes, we need 3 filters. So each of these is a 1-layer StaRS filter, which means that there is 1 influent stream and 1 effluent stream, as opposed to previously we had a 2-layer StaRS filter where there was 1 influent stream and 2 effluent streams. Additionally, when we were fabricating our filters, we had to take into account the backwash. So there's a backwash process that we have in this apparatus where water flows up from the bottom to the top of the filter, and when this happens, the sand in the filter gets pushed up and it's fluidized, and basically the sand becomes 1.5 times its original height. So our plan for the 1-layer StaRS filters was to make them 20 centimeters in height, which means during backwash they become about 30 centimeters in height. Basically, we decided to make our filter columns 40 centimeters just to make sure we're on the safe side. Additionally, we made them out of PVC and we modeled them after our previous apparatus.
So the next part we had to fabricate were our 3 inlet pipes. So the 3 inlet pipes were made out of brass, whereas the prior apparatus had them made out of copper, and we don't actually believe that will have significant effects on the system. And so then they also have a capped end so that the water has to come out into the filters through this orifice that we also had to make. So one of our biggest challenges was trying to figure out what size to make this rectangular orifice. So there is an equation for maximizing the size of the orifice with efficiency. However, we aren't actually sure the full extent that it will have, or the extent of the effect it will have on our filters, so we ended up just doing the same size as the previous apparatus. So this is the orifice on our current inlet pipes, and it's mimicking the shape of the orifices on Agua Clara plants as they were when the original stacked rapid sand filter apparatus was built.
And additionally, we fabricated 3 outlet pipes, which follow similar geometry to the inlet pipes. They are 0.5 inches in diameter and 10 centimeters in length. And the end that is inside the filter is soldered with mesh, and this prevents sand leaving the filter.
We also fabricated the top of the filter, so this sits at the very top of the PVC pipe, and that is where water flows through during backwash. And to make sure that sand isn't leaving with our backwash stream, we also had to put mesh on the inside of this part.
So another task that we did this semester was obtaining the 3 different sand grain sizes. And this we were able to sieve the sand that we had with the help of the Cornell Center for Material Research, which is found at the bottom of Bard Hall. And previous teams have used the mesh size between 25 to 35, and as we are varying diameter side, we want to look at sand sizes that are smaller and greater than the previous teams have used. And we were able to sieve the sand using this machine, which is a vibrating sieve machine, and it just helped our process significantly. Here are some visual aids to see clearly how the sand's diameter is varied. So, as we were focusing with fabrication this semester, we did not run any experiments. That will be our main focus for next semester. Additionally, we still need to find tubing, pumps, and turbidimeters to finalize our current apparatus setup.
And so the next step for the next semester team will be to write new Procoda methods. So the new Procoda methods will have to take into account the 3 apparatuses, or the 3 filters. So there will be a pump that has 3 heads to cause backwash, and also 3 effluent turbidimeters to measure the turbidity out of each filter.
And then after we write our Procoda methods, we will begin running experiments. So as we mentioned earlier, previous teams in the past have focused on varying coagulant dosage and seeing how that affects filter efficiency. So we will continue running those experiments, but with our 3 new filters and seeing how coagulant dosage and sand grain size affect filter efficiency. And we predict that our major challenges will be writing our Procoda methods because all 3 of us have very limited experience with Procoda. And our second challenge that we expect will be making sure that the filter and the apparatus are all waterproofed and that we don't have any leaks in the system. Thank you.
Thank you for watching our presentation.
Alrighty, under 10 minutes.
Yay.
Do I just?
You press the...
I'm just a high press trash.